Okay, so today's announcements are just that the Chapter 8 sapling is still going to be due Monday, 9 a.m. I figure I've done almost all of the chapter by now except for the last paragraph or two. So this way we have it due before the exam, so that's going to be helpful. And then Chapter 9 sapling is going to open up today, so you get a chance to work on it well in advance of the exam. Okay, questions about those? Okay, cool. So where we left off last time is looking at solvent properties. And so just to wrap up that topic, so hopefully you remember from lab or from Gen Chem the concept that like dissolves like. So the more common properties there are between the solvent and whatever you're trying to dissolve, the solute, the more soluble it's going to be. So when they're more soluble, similar to the solute. Okay, so if you remember in oxymercuration, we used mercury acetate and water and an alkene, and we had to use THF to sort of tie it all together, just because THF is sort of a good intermediate property solvent. It's got some things in common with water and some things in common with the alkene. Okay, so here's an example. In water, these two compounds are insoluble. And by the way, it's sort of a bit arbitrary where we draw the cutoff between soluble and insoluble, but, and it also varies from source to source sometimes. But basically, you can get a lot less of these compounds per volume dissolved into water than you can this one, for instance, diethyl ether, which is soluble, soluble in water. And even that has limits when you try to pack too much of it in there, unlike this, which is miscible. Okay, so the difference between soluble and miscible is soluble eventually you hit a point where you can't fit any more into solution. Miscible means infinitely soluble. So no matter what ratio of water and propanol you mix together, they'll still mix just fine. They won't separate out. All right, so miscible just means literally mixable. You can mix them together in whatever proportions. Okay. So questions about this? Okay, cool. So the more compounds have in common with the solvent, the better they're going to dissolve or mix with them. So you'll notice that this one, just like water, is both an H-bond donor and acceptor. And so it can really get along with water. It can H-bond sort of in either direction with water. This one is only an H-bond acceptor, so it can only pick up protons from water, but it can't donate any of its own. So it's got some in common with the solvent, but not a ton. These two are just completely different from water, and they're not going to mix with it very well. Question?
So are most alcohols mostly miscible?
Excellent question. That leads me to the next point in the notes. So how common do they have to be before you start running into solubility issues? So let's look at, Okay, so 2 carbons, 3 carbons, 5 carbons, and 6 carbons. We're going to skip 4 just because I got the data for these ones. Okay, so these two are miscible in water. this one is soluble up to 7.7%. I think this data is for room temperature. Obviously, that's going to change at higher or lower temperatures. And this one is soluble up to 0.6%. So just by adding that sixth carbon in there, suddenly we cut solubility way down by like more than an order of magnitude. So what's going on here? All four of these have something in common with water. They're both H-bond donors and acceptors. But you can kind of think of it like by the time you get up to 6 carbons, the alkyl tail of the molecule, like this really dissimilar from water part, is sort of starting to outweigh the behavior of the one good part that can interact with water. So it's sort of a conflict between like, is the alkyl chain dominating its solubility properties or is the OH head group dominating its properties? And at this point, the alkyl chain, I guess, ends up taking priority. So you wouldn't be able to know like the actual numbers just from looking at these, but you could look at the structures and say, okay, this one is going to be harder to dissolve in water than this one, which is harder than these two down here. Okay, questions about those? Yeah?
Can you clarify exactly what soluble up to 7.7%? Does that just mean 7.7% of the mixture can be?
Exactly, yeah. Okay. Yeah, so in water, yeah, about 8% can be that compound. Okay, so other questions about this trend? Okay, so I guess in terms of practical applications, if you're trying to dissolve both polar and nonpolar compounds together, say like water and an alkene, then a mid-range polarity solvent is a good choice. So some real common good ones are THF, DCM, and acetone. All right, those of you taking lab, you already know acetone's pretty much good for anything. It gets organic corrode off your glassware, and it also gets water off of your glassware too. So acetone is like a really good solvent to use. The downside is acetone has a carbonyl in it, a CO double bond, which, as we'll learn for most of OChem 2, actually does a ton of reactions of its own that may cause problems. So THF and DCM tend to be less reactive and less likely to cause problems. Okay, any questions about that? Okay, cool. So that's all I got for chapter 8. It's a pretty short chapter. Chapter 9, by contrast, is kind of a behemoth. Okay, so I mentioned that 8 introduces a bunch of functional groups, and then 9, 10, 11 sort of go into more depth on each of them. So 9 is where we're going to start getting into alkyl halide chemistry. Okay, so this is useful because these do like reactions that we'll also see in a slightly more complicated context in the chapters after this as well. Okay, so except for the last couple reactions at the end of the chapter, which we may or may not get to before the exam, we'll see how we go, most of the bulk of this chapter really only covers 2 different types of reactions, just goes into a whole bunch of detail on both of them. So all of what we're going to do in this reaction, in the first part of this chapter, is either substitution. So if we have, remember, X is a halogen, and we bring in some kind of nucleophile, which remember is Nu for short, what we can do is actually substitute the halogen for whatever that nucleophile is. We're straight up swapping out one group for another. Okay, so that's one type of reaction that we're going to see in this chapter. The other type is, if we start with exactly the same alkyl halide, what we can do instead of swapping the group out is actually taking advantage of something that's one carbon away. So for describing sort of the location of functional groups, a lot of the time we'll say, okay, the carbon where that group is attached, we're going to call the alpha carbon. Then the next carbon along is the beta carbon. And then gamma, then delta, then so on through the Greek alphabet. But usually alpha and beta are like the most important for what we're looking at because they're the closest to where the stuff's actually happening at the molecule. Okay, so this would be the beta carbon to the alkyl, or to the halogen, which means any H's attached to it are beta hydrogens. And it turns out if you hit this with a base under the right circumstances, you can do what's called an elimination. So what's going to happen, specifically a beta elimination. So we're going to pull off the H at the beta carbon. We're going to pull off the halogen. And we're going to form a double bond between them. Okay, so notice that this is actually like conceptually pretty much exactly the opposite of what we did in chapters 4 and 5. There we started with an alkene. We added something to one carbon, we added something to the other carbon, and we got rid of the double bond. Here we're going sort of backwards, although it turns out like the details are totally different. We're pulling an H off of one carbon, we're pulling a halogen off of the other, and we're forming a double bond between them. Okay, so that's sort of the big picture of how most of this chapter is going to work. The details are a lot more complicated depending on exactly which type of substitution or which type of elimination we're going to do. Okay, so before we get into that, let's do just a little bit of terminology here for things that are going to come up. I guess not all of these are new, but just to put them in the one place. Okay, so the substrate is sort of a general term for the molecule that is having a reaction done to it. So in other words, for this chapter, it's always going to be the alkyl halide. Okay, so that's our Rx molecule for this chapter. The leaving group is whatever the group is that's dropping off the molecule and taking electrons with it. So that's often abbreviated as LG for leaving group. And that's a group that's leaving with a negative charge or with the electrons out of the bond. So in this case, for this chapter, it's always going to be a halide, like an X minus. Okay, and then the other molecule, whatever is written on the arrow for these reactions, we're going to describe it a little bit weirdly. What we're going to call it is the base/nucleophile. And the reason we're sort of combining those terms, or leaving it vague which one of them we're using, is because the same molecule can actually do either job depending on context. So so this is the compound that actually does the substitution, which would make it a nucleophile. I guess more to be specific, if it's acting as a nucleophile in that particular situation, it's going to do a substitution. or that does the elimination if it's acting as a base. Okay, so one example of things sort of being able to pick and choose either job is this particular setup for reasons that we'll explain later on in the chapter. Say we're using ETO minus here. This one can do sort of a mixture of substitution, where you swap out the halogen for an OET group, and elimination. So you're going to get both products mixed in together here. So sort of the important message here is that whatever is written on the arrow, or whatever the base nucleophile is, it's sort of got like two separate sliders, I guess, for like how good a base is it, in which case that'll determine how easy it is for it to do elimination, and how good a nucleophile it is. And we can look at sort of being able to figure that out based on context later on. But in this case, it turns out to be pretty evenly balanced between its nucleophile ability, or its nucleophilicity, and its basicity, which means that it's actually going to do both reactions in competition with each other. Okay. So a quick side note about the way I wrote things on the arrow. Note that stuff like this I can write as the bare anion. So for instance, this one is an ethyl group attached to an oxygen with a minus charge, which is ETO minus, or ethoxide. Or you can write it with a counter ion, because that's how you would actually put it into the reaction. For instance, ETONA, ETOK, or you might see it flipped around like NaOET. These are all just different ways of writing the same thing. The actual like part of the molecule that's doing the chemistry is the ETO minus. If you see it attached to some metal atom, say like sodium or potassium, remember that this is an ionic compound, and that's just going to drift off with a positive charge and not actually do anything. So anytime you see something attached to a metal, assume that whatever the rest of it is has a negative charge on it, and that's what's going to be doing the chemistry in this chapter. Okay, so we can see this for like alkoxides, like this one are real common, but we can see them for like pretty much anything. So like, I don't know, NaOH, you would assume that OH minus is doing the actual reaction. NaNH2, it's really OH minus. NaNH2 is really NH2 minus. So I know this is kind of like, if you remember about ionic compounds, you should already know that, but this is kind of a common place where people just don't sort of think to check that, and so it's easy to get tripped up before you've really even started looking at the reaction. Okay, questions about those? Okay, cool. Okay, so one thing that's going to come up a fair bit in this chapter, which we're going to just dip into a little bit here, is if you remember reaction kinetics from Gen Chem 2, looking at rate order equations and stuff like that. Turns out that actually was sort of a big factor in how people figured out all of the stuff in this chapter, because different versions of substitution are going to follow different rate laws. So let's take a really quick look at reaction kinetics. Okay. So say we're looking at some real general example, maybe like A plus B is reacting to form C. the rate of a reaction is always given by how fast you're making C. So rate is given as change in product concentration over time. And if you remember, we use square brackets around the name of something to indicate its concentration. So we're looking at the change in the concentration of C over time. And it turns out that we can write sort of a general equation to describe this, which is some constant, K, times concentration of A to some power, let's call it N, times the concentration of B to some power, let's call it M. Okay, so this is leaving it real vague as to like how much A influences how fast the reaction goes and how much B does. And there's a ton of different possibilities here. So I just did a table in the notes with some possible ways that this could look. Okay, so basically the way you feel this out in the lab is you try doing the reaction once and then you double the concentration of one of the reactants, say you put twice as much A in there, and then you see like how fast the reaction goes compared to the first reaction. So so doubling the concentration of A sorry, I'm just trying to figure out the best way to squeeze all this in the board. Okay. Okay, sorry, there's a lot going on this table. Okay, so I got 4 different things that I used for examples here. Okay, so say we do this reaction. We play around with the with the concentrations of A and B, and we find that doubling A doubles the rate. So in other words, we put in twice as much A, it goes twice as fast. We also figure out that doubling the concentration of B does nothing. No matter how much we put in there, the reaction rate doesn't change at all. Then we know that this is going to be proportionate to A to the first power, so N is going to be equal to 1. M is going to be equal to 0 because B straight up doesn't factor into the rate for the equation at all. So the rate law for this one would just be K times concentration of A. Okay, so the overall order, we just want to sum up the powers of all the reagents. So N plus M, 1 plus 0 is 1. And based on the overall order, we can describe the reaction type as unimolecular. So whatever's going on in there pretty much involves just a single molecule at whatever point is setting the rate for the reaction. If you remember from Gen Chem, there's the rate determining step. Actually, yeah, we covered kinetics a little bit when we were looking at alkenes. So whatever the rate determining step is for this reaction only involves a single molecule of A doing something. Okay, so questions about that example? Okay. All right, cool. So a few more examples here. If we figure out like take a totally different reaction that also follows the A plus B goes to C pattern. And on this one, we're playing around with it in the lab. We figure out that doubling A also doubles the rate again, and doubling B also doubles the rate. That's telling us that I guess the rate scales proportionately to the concentration of A. So N is going to be 1. M is also going to be 1 because B is now proportionate to the rate. So that's 1 and 1, which gives us a rate law of K square bracket A square bracket B. Okay, so again, we can add those exponents. 1 plus 1 is 2, which means that whatever's happening at the rate determining step here involves one molecule of A doing something with one molecule of B, which would make this a bimolecular reaction. Okay, questions about that or about the difference between the first two? Okay, cool. All right, so two more examples. All right, take a totally different reaction again with different molecules. We're playing around with it in the lab. We figure out that if we double the concentration of A, we're going to quadruple the rate. Then we play around with B. Doubling the rate does nothing. That tells us that when we double the concentration of A, we're getting 4 times as much speed out of this thing, which tells us we're squaring whatever the concentration of A is. So N is going to be 2. And meanwhile, just like in the first example, B does nothing. It's going to be 0. So our rate law is going to be Ka squared. Overall order is 2, which means that this is also one example of a bimolecular reaction. Because again, there's 2 molecules involved at whatever the rate determining step is. They just both happen to be A doing something to another copy of A. We have no idea what yet. Okay. So last one. Say we have doubling A quadruples rate and doubling B doubles the rate. That tells us that N is going to be 2, M is going to be 1. Our rate law is given by K A squared B. And our overall order would be 3. This would be an incredibly rare example of what's called a termolecular reaction. I can't even think of any of these off the top of my head, but I'm not even sure if the name got come up with is kind of like a hypothetical if you had something that relied on 3 molecules all coming together at the right time. Termolecular is just so statistically unlikely that I don't think you'll ever see it. Pretty much what's a lot more likely to happen is either one molecule does something on its own, or we're just waiting on 2 molecules to bump into each other. Termolecular means we're kind of waiting on 3 molecules to all bump into each other at the right way at the same exact instant, which is obviously kind of unlikely. So, okay. So, questions about any of these 4 kind of hypothetical reactions? Yeah.
So these reactions are like a reaction that happens at one time, like 2 molecules come together at the same time.
Exactly. So bimolecular means that whatever's happening at the highest energy point on the diagram, the rate determining step, it involves 2 of them crashing into each other the right way. So,
Do you ever have 4 molecules?
Oh man, so like 3 is already hard enough. I don't even know, like if it did exist, it would just be like so slow that we wouldn't even consider it a reaction, I bet. Yeah.
So if you had like a reaction in which 2 molecules reacted and then like another molecule reacted with that new product, would that count as like 1 bimolecular and 1 unimolecular?
So all of this is just based on what's going on at the slowest point of the reaction, the rate determining step. And so in that case, if you've got like something that's multiple steps where like maybe the first one involves one molecule and the second step involves two, then it just depends on which one's the slowest. Because all of this is just bottlenecked by like what's the hardest step for the reaction to do. So that actually kind of leads me into the next part that I'm going to write up here. So rate depends on which molecules are involved in the rate determining step. So this is the slowest step of the reaction, whatever it is, and it's the one where you go through the highest point on the energy diagram. Okay, so if you remember when we looked at this in the context of alkene addition reactions, a lot of the time there, our rate determining step was making a carbocation because that was really tough and we had to go uphill in energy a lot. That's actually going to show up as the rate determining step for some of the reactions in this chapter as well, making a carbocation just by a different process. Okay, so yeah, all of this is like unimolecular means one molecule is involved in doing whatever the rate determining step is. Question?
So if you triple the rate by doubling and raise it to 3 halves?
Ooh, in theory, but I have no idea how that would work on a molecular scale. Yeah, because then it would be like 1.5 molecules of this are doing something and yeah, I don't know about that. Okay. Okay. So we could describe, for instance, the first reaction up here as unimolecular in A. Which means that a single molecule of A is doing something during the rate determining step. Whereas bimolecular for A and B means that the rate determining step involves one of A and one of B getting together and doing something. Okay. So we've looked at, in this sort of general equation up here, K equals A to the N times B to the M. We've looked at N and M and played around with those. We haven't really looked at K, and we're honestly not going to that much. But just as sort of a quick side note here. So this is called the rate constant, K. And again, you're probably pretty sick of seeing that if you've taken Gen Chem recently. But kind of like you'd expect, the bigger K is, the bigger the rate's going to be based on this equation, which means the faster the reaction's going to go. So bigger K gives faster reaction. So can we play around with K at all? Turns out, yeah, we can. K is like, for a very specific example of a reaction, it'll have a particular value of K under a given set of circumstances. But in general, K is determined by two main factors. One is the delta G double dagger of the reaction, which we saw a little bit in chapters 4 and 5. So this is the activation energy, how much oomph you have to give the molecules to like push them up that hill on the energy diagram. All right, there's a whole equation for determining the relationship between K and delta G double dagger. Honestly, not that useful to get into for the context that we're looking at. So smaller activation energy means bigger rate constant. So in other words, just to do a quick sketch here, if you've got two different reactions available to you, and one of them involves having to get over a much bigger barrier, so the bigger the delta G double dagger is, the harder it's going to be for the molecules to get enough energy to get over that barrier, and the slower the reaction's going to go. So the rate constant is going to be smaller. Okay, so that's one factor, and then another is how much energy are you pumping into this reaction in the form of heat. So higher temperature will also give a bigger K. So if you want your reaction to go faster, in other words, you can either tweak whatever the conditions are so that the barrier is shorter and easier to get over, or you can give the molecules more energy, give them a boost over that hill, and then the reaction will also go faster that way. Okay, so we're going to see only a little bit of playing around with temperature to tweak the reaction outcomes, but this is kind of the general idea here. I think in chapter 4 we mentioned that as kind of a general rule of thumb, adding 10 degrees Celsius about doubles the rate of the reaction. But yeah, we don't really have to worry about specifics there. Okay, so why are we digging into this Gen Chem 2 review? So let me erase part of the board and then I'll show kind of what we're looking at. Okay, so it turns out that out of the two basic types of reactions I showed for this chapter, substitution and elimination, we're actually going to see one example of a unimolecular substitution, one bimolecular substitution, one unimolecular elimination, and one bimolecular elimination. So we're sort of looking at a 2x2 grid for most of this chapter. All right, so the four reactions that make up most of this are SN2, which is bimolecular substitution. We're going to look at SN1, which is unimolecular substitution. we're going to look at E2, which is bimolecular elimination. And we're going to look at E1, which is unimolecular elimination. All right, you might be asking, where's the N coming from? That actually stands for nucleophilic. Turns out, much later on when we start looking at aromatic rings in OChem 2, we can look at electrophilic aromatic substitution. So this is nucleophilic substitution. I think it was mostly discovered by the French, who named it, I think, substitution nucleophilique, first order, but so that's why, so capital N and then capital N that's like a subscript, and then either a 1 or a 2. Okay, so this is kind of a roadmap of what we're going to be looking at for most of this chapter. First, we're going to dive into details on how each of these reactions work, what's happening on a mechanistic level, and then we're going to put it all together and say, like, okay, for a given set of reagents that you have, how can you figure out which of these reactions is going to be most favored, and then show it happening to the molecules that you're given. And sometimes it's going to be a mixture, like you might get a mixture of SN2 and E2, which is kind of this example that I drew way up at the top here. It turns out to be an SN2 E2 mix under these circumstances. Okay. So I think that's actually a good place to stop because I don't want to get right into SN2 right away, but I'll pick up there on Friday.